We're going to do a lab today, the purpose of which is to find the spring constant of a particular spring. So the problem, phrased in the form of a question, would be something to the effect of, what is the spring constant of a particular spring? We're going to have three variables, of course. The manipulated variable, of which there is one. That should become relatively evident, I think, as we go through the procedure. Similarly, we'll have one responding variable, which should become, I think, pretty evident to you as we go through the procedure. And then the control variables, of course, we're going to have, thousands of control variables, but there's going to be one or two really important control variables, and those are the ones, as always, that I expect you to list. Okay, I'm not going to put a number on that. I just want you to list everything that's really important. I don't care if you list the temperature of the room has to stay the same, even though technically it should. Okay, what I want is what's really important. If I change this, then it's going to completely mess everything up in this lab. Okay, write those out as your control variables. The materials, there's not much as far as materials go. You have this apparatus here, which is called a Hooke's law apparatus. Hooke, by the way, is spelled H-O-O-K-E. A Hooke's law apparatus. Now, attached to your Hooke's law apparatus will be a spring. Now, you're going to find that that spring should be inside the box, probably inside a bag like this, in the box that your Hooke's law apparatus is in. But it comes separate, so we're going to list it separately. You've got your Hooke's law apparatus, you've got your spring, and you've also got, although you don't see it here, you've also got a mass set that you're going to use in conjunction with your spring in your Hooke's law apparatus. And that's effectively it for the materials. Now, how are you going to perform this lab? The first thing that I want you to do is put the spring on the hook. And you put a spring on a hook right up here at the top of your Hooke's law apparatus. Now, you're going to find when you do that, that the bottom of that spring may or may not be lined up with the 0 mark on your ruler. You want it to be lined up with the 0 mark on your ruler like it is right here. You see this? Okay, this is lined up with pretty much, almost, with the 0 mark on my ruler. If it's not lined up, then what I want you to do is pinch the back of that ruler with both fingers, and you can raise it up or down until it is lined up perfectly with the bottom of your spring. That's going to be where you measure from, the bottom of your spring. Now, once you have it set up like this, you're going to take one of these green mass sets, open it up, and there should be a hook where you put these masses, where you slide these masses onto the little slot mass apparatus. You're going to, well, first you're going to take off all of these masses so that it's basically empty, just basically the hook and the one mass that's attached to it at the bottom, and then hook it onto your spring. And you're going to measure from that what your displacement is. You can see if I had this zeroed, my displacement is now to the bottom of this hook 3 centimeters. I'm going to record whatever mass I was using, and I'm going to record the displacement that occurs as a result of changing that mass. And then I'm going to add more mass to it. Put one of the slot masses back on and see what the displacement becomes now. And then I'm going to put another slot mass back on and see what the displacement becomes now, and so on and so on and so on. So I'm going to add at least 10 different masses. And I'm going to see what the 10 corresponding displacements are. Then I'm going to create another table, an analysis table. Instead of mass and displacement, it's going to be force and displacement. How do you think I'm going to find the value of that force? The applied force, the amount of force that was applied onto that spring. Yep. Good. It's mass times gravity. You're going to have to make sure that when you do that, your mass is measured in kilograms. And notice my displacement here is measured in meters. Back here in your data table, it doesn't really matter what units you're using. But when you create your analysis table, I want you to be in newtons, which requires you to use kilograms, and I want you to be in meters. Because you're going to plot a graph from this, and in your graph, you definitely want to be in the proper units, meters and newtons. My graph will look something like this. It's go back to my table actually for a second. Which variable is going to appear on the x-axis, force or displacement? Yep, force. The first column of your table is always the x-axis of your graph. So this is going to be force in newtons, and this is going to be displacement in meters. You have to title this as well. Be careful you make it y-axis versus x-axis. When you do this, you should get a nice straight line. Now, we've gone through an analysis once before on how to find what the slope of a graph represents. We're going to do it again today. In Physics 30, we're going to do it about 10 times. Okay, this is going to set you up, give you guys a little bit of a head start on how to do this analysis, this graphical analysis for Physics 30 that we have to do quite often. I want to see what the slope of a graph that I've never seen before represents. I'm going to start off with an equation that describes any straight line graph. That's what I have here, right? Straight line graph. What equation describes any straight line graph? Think back to grade 9 math. Yep. Yeah, close. Y is equal to mx plus b. Remember that, guys? It's not just this graph that's represented by that equation. It's any straight line graph that's represented by this equation, y equals mx plus b. Then what I want to do is replace y with whatever appears on the y-axis. Displacement is on my y-axis. Now, this is a little bit confusing because displacement is what variable? What symbol? What symbol did we use yesterday to represent displacement? X. We're not replacing y with x because the axes switch. We're replacing I with x because that's what displacement is x. M is the slope. I'm going to write the word slope. It's already confusing enough that y became x. If I don't write the word slope here, then at some point I'm probably going to get mixed up between mass and slope if I keep calling it m. The x-axis is force. You can see on the x-axis here that it's force. And the y-intercept, b, the y-intercept, well, you can see it's pretty much 0. And you should see on your graph as well when you go to plot it that it's effectively 0 through the origin. Pretty close. Then I want you to find an equation that has x and f in it. What equation would that be? We just did it yesterday. Hooke's law, what is it? Yep, Jen? Yeah, let's just say F is equal to kx because we're actually talking about the applied force as opposed to the restoring force here. So instead of negative kx, we'll only get positive kx. Let's rearrange this to solve for x because that's what I did in this equation. X is equal to F over x. Or sorry, F over k. Now I'm going to go one more step. I don't really have to, but I'm going to. Do you agree that this is the same thing? F is equal to 1 over k times F is the same as F over x? I didn't need to do that. Okay, if you didn't do that step, that would be okay. But you'll see in a second why I did that. I'm going to cross off now things that appear in both equations. X appears in both. F appears in both. What am I left with? Slope is equal to 1 over k. Now, I could have done that up here. X disappears, F disappears, F disappears. What am I left with? The slope is equal to 1 over k. It's just a little bit easier, I think, in this one to see that it's 1 over k. So my slope is equal to 1 over k. If I want to find k, which remember was the whole point of this lab, to find the value of k, what am I going to do? 1 over the slope, isn't it? Just take the k up, the slope down. Whatever you get for the value of the slope, flip it over. And that's the value of k. So whenever you get your value of slope from Google Sheets, and remember the formula that's going to take, right? Up here in the top right-hand corner, it's going to say something to the effect of 0.721x plus 0.004 or something like that. The number that you want is this one. That's the slope. Take the inverse of that, and then that's going to give you the spring constant of this. Now, I want you to show not only the inverse of the slope gives you the spring constant, but I want you to show this analysis as well. Even though I've done it for you, okay, and I know, I'm fully aware that when you go to put this into your lab write-up, you're going to copy this exactly as I have it here. So what's the point of it? Well, there's value in you writing it. Okay? At some level, you internalize it just a little bit more when you write it. So I want you to write this out. If you want to write it out by hand and then snap a picture of it and put it into your lab write-up, that's okay. Or if you can do it on right into Google Docs with the keyboard, that's fine too, whatever works for you, okay? But I do want to see this analysis. I don't want to just see the calculation. I want to see how you arrived at that, even though it was me that showed you how you arrived at that. Maddie, question?
I was just going to say, could we not just find K like above the graph? Just move the data?
No, that's a good question though. The question, if you didn't hear that, was couldn't we just find K from the data as opposed to from the graph? If you went back to your data here, you could calculate K, so K is equal to F over X, right, for each of these. But that's going to give you a value of K here, and another one here, and another one here, and another one here, another one here. Okay, the problem with that is that if you happen to be off on a data point or two, then you get a dramatically different value for Hooke's spring constant, right? The point of a graph is that it kind of smooths it out. Okay, I get a data point that's way up here, but I get another one that's way down here, right? And if I draw a line of best fit like this, it kind of takes care of the inconsistencies in the data. If I calculate each of these, then this one, first one could be way off. They all could be way off. But when I plot the graph, it kind of averages it out in a sense. Does that make sense? Okay. Yeah. Question, Carl?
Can you just take the mean of all those numbers?
You can, but that's not the best way to do it. The graph is definitely the best way to do it. But that is one way that an analysis can be done. I just don't want you to do that because it isn't the best way. The accepted practice would be to plot the graph and to take the slope of that graph. Next comes your conclusion. Your conclusion, of course, is, well, what did you find? The value of the spring constant is whatever, and then how do you know? So justify it, essentially. This is the value of the spring constant, 25 newtons per meter. This is known because the inverse of the slope of a displacement versus force graph gave me this. Then, of course, your sources of error. You want usually 3 good sources of error, along with suggestions for improvement. How can we make this better another time? Or what did you do midstream to make it better, to fix it?